Old legacy processors brute force. An instruction enters the processor as a series of jagged voltage pulses. These pulses represent ones and zeros. The chip receives them as abrupt high and low electrical states that must be interpreted by the control logic. The control logic begins decoding the instruction. Inside the chip, thousands of tiny transistor switches flicker rapidly. Signals split and branch through a dense maze of metal lines. Every decision requires physically forcing electrons through these gates. The processor fetches data by pushing electrons down long metal interconnects. These pathways glow with electrical activity. Resistance builds, heat forms, and noise appears as electrons collide and scatter while traveling to memory and back. Computation occurs inside the arithmetic units. Millions of switches flip on and off in rapid succession. Electrons bounce, leak, and jitter as the processor forces each operation to complete. Every calculation is a physical shove against the hardware. The result is pushed back through congested return lines. These pathways glow red from heat buildup. Noise spikes appear as the system struggles to maintain clean signals while routing the output back to storage or the next instruction. The entire chip shows hotspots, jitter, and chaotic electrical activity. The architecture is limited by resistance, heat, and the physical cost of switching millions of transistors every cycle. Harmonic phonons-based processors. An instruction enters the processor as a smooth harmonic pattern. Instead of voltage spikes, the information is encoded in frequency and phase. The incoming wave carries structured meaning without abrupt electrical transitions. The harmonic control layer locks onto the incoming frequencies. The central cross structure lights up with synchronized waves. The processor tunes itself to the instruction rather than forcing electrons to switch states. Data is accessed through resonance matching. Memory regions begin vibrating in sync with the control frequency. Information transfers naturally when the frequencies align, without pushing electrons through resistive pathways. Computation occurs where harmonic lines intersect. When two or more frequencies meet, they form a new stable interference pattern. This pattern represents the result of the operation, created through harmonic interaction instead of switching. The resulting harmonic pattern flows along aligned pathways. The output wave moves smoothly through the processor with no jitter, no heat spikes, and no resistance. The system remains coherent throughout the process. The entire processor glows with calm, synchronized waves. Every part of the system remains in phase. The architecture works with natural harmonic behavior instead of fighting physical limitations. This concludes the internal walkthrough of the Aurora project and its integrated immune architecture, the Artified Biological Life Immune System, ABLIS. You have now seen the complete operational contrast between legacy, electricity-driven processors and Aurora's harmonic-driven computational model. Traditional systems rely on voltage transitions, transistor switching, resistive pathways, and thermal load. Aurora operates on harmonic alignment, resonance-based data access, frequency-driven computation, and coherent signal propagation. By visualizing both architectures from the inside out, you can now see the structural differences that define their behavior. One system fights physics, the other uses it. One depends on force, the other depends on alignment. ABLIS maintains coherence, stabilizes internal states, and preserves system integrity under all operating conditions. This is the Aurora project, a processor defined not by switching events, but by harmonic structure. A system that computes through resonance, protects itself through alignment, and maintains operational certainty through the continuous action of ABLIS. Now you understand the architecture from the internal mechanisms to the system-level behavior. This is how it works, precisely, structurally, and completely. The immune layer in this architecture is formally named the Artified Biological Life Immune System, abbreviated as ABLIS. The name reflects its function, an artificial system modeled on biological principles of stability, alignment, and self-correction. Artify defines its engineered origin. Biological life defines its behavior, pattern, continuous monitoring, pattern recognition, and structural preservation. Immune system defines its role as the protective layer that maintains coherence across all harmonic operations. ABLIS is the component that stabilizes the Aurora project's processor, detects misalignment, and restores harmonic integrity in real time.